Today, I will be talking about data-driven pricing on a common data structure, which are conversion rates. And more specifically, we're going to focus on the case where we observe a single conversion rate, hence the title of the talk. This is a joint work with Professor Omar Besbes from Columbia Business School and Amine Allouah from Facebook Core Data Science. So let us start with a concrete motivating example here. Let's suppose that we have a seller, for example, an e-commerce or a retailer who has been offering a single product at a fixed price for a period of time. So for example, for a quarter, the product was available to customers at the price of $2,800. And the seller during this period observed that 1,000 users browsed the specific product page, and only a fraction of users actually made the buy decision. So for example, here, 50% of the customers actually bought the product. Now, the seller for the next quarter has the opportunity to update her price based solely on the data collected during this quarter. So let's ask a couple of questions here. What is the data available to the seller right now? It's just the buy or no buy decisions made by customers at the fixed price during this period of time. Therefore, the seller can only estimate the fraction of customers who have a willingness to pay higher than the historical price. So in other words, the seller does not have any sort of price elasticity information or any demand sensitivity with respect to the price, as the price the posted price was fixed during this period. And now the seller has to exploit only this information in the best possible way in order to maximize her revenue. So what I want you to keep in mind from this example is that, first of all, this data structure is fairly typical in practice. And sellers usually hold prices fixed for a long period of times and observe this kind of data structure. The second important point is that we don't have any price dispersion or any elasticity information at all. And lastly, from a theoretical perspective, this is a fundamental building block to understand how we can conduct product pricing with measurements with limited price points and understand the value of these limited measurements. So let's go back to data-driven pricing in general. So obviously, pricing is central across many industries, ranging from retail to transportation. And at the core of pricing algorithms that are used to automate pricing, there is this concept of willingness to pay of customers, where this theoretical quantity is rarely available in practice, but we only have access to it through signals that come from the data that we collect about the customer behavior. And the goal of all data-driven pricing algorithms in general is how to go from these signals and from this data to pricing decisions. So in this talk, we're going to specifically focus on the case where the available signal is just the conversion rate at a specific price point. So let's start with a sample of related literature. So this work is related to various streams of research in the operation research community, economics, as well as computer science. So a first related stream of literature is where we know some information about the support of willingness to pay distribution or some statistical information, for example, the mean or the standard deviation. Another related stream of research is where we know some we have access to signals of the willingness to pay through samples that are, for example, obtained from market research. And finally, a third related setting is where we price while we learn and where we are interested in characterizing the long-term or asymptotic performance of our pricing policies. But the main takeaway is that, to the best of our knowledge, there is no systematic understanding of the value of a single measurement and how to exploit it for pricing purposes. So now let's formulate the problem. So the problem is fairly simple and elegant to state. So let's consider just one seller trying to sell one indivisible good to one buyer. The buyer has a willingness to pay distribution F with support positive numbers corresponding to prices. The seller does not have access to F, but only has access to one single information about F, which is the conversion rate at a specific price point W that has been fixed. And we will be considering two main cases: the case where the seller knows exactly this number, and also the other case where the seller has some confidence interval about this quantity. But for the sake of simplicity and time in this talk, we will focus only on the case where we know exactly this conversion rate, but our results extend also to the other case. And the seller also knows that the distribution F belongs to some broad non-parametric set that I will specify later on. And the seller is considering implementing two types of mechanisms, the randomized mechanisms and also more simpler mechanisms, which are deterministic mechanism, where the seller will commit to a single price to post. Now, so if the seller is decides to implement a mechanism psi and the willingness to pay distribution of customer is F, then the expected collected revenue is just going to be the weighted sum of the expected revenues as each price point weighted by their posted probabilities. And we will compare this collected revenue to the optimal revenue if we knew the full distribution. And we will quantify the performance of a mechanism against a class of willingness to pay distribution by the worst expected ratio against all distributions belonging to this class and satisfy the information that we have observed. And our goal here is to find the best mechanism that yields the highest worst expected ratio. So this maximum quantity here is a number that is between 0 and 1. The closest to 1, the better, and allows us to characterize the value of information that we have observed. Now let's go back to the class of distributions that I mentioned earlier. So we're going to consider two main classes. The first one is regular class of distribution. So this class is fairly popular in pricing literature, and it is characterized by the revenue function being concave in the quantile space. The second class is monotone hazard rate distributions, which are characterized by having a monotone hazard rate. And this class is a subset of the regular class and have more constrained tails by exponentials. But I want you to keep in mind is that these two classes are broad, they are non-parametric, and include most of the fairly popular distributions such as truncated normal, exponential, linear, etc. And our framework is actually general and applies to a generalized class named alpha strong regular that admits these two classes as special cases. For alpha equals 0, it corresponds to regular, and for alpha equal 1, it corresponds to MHR. And you can think of alpha by a parameter that quantifies by how much the tail of the distribution is constrained. So before presenting the results, let me summarize the main contributions. So first of all, we develop a bottom-up approach to pricing by characterizing what is the best we can do with this available single conversion rate data. And we give a resounding yes to the question of whether one can actually price without any derivatives. So we develop a unified framework across the distribution classes that I just mentioned and show a full characterization of the optimal performance of deterministic mechanisms in closed form. So in other words, we provide an explicit mapping from the information at hand to the optimal performance and the optimal deterministic mechanism to implement. For randomized mechanism, we develop a sequence of linear programs that allows us to fully characterize the optimal performance and the near optimal randomized mechanisms. The obtained results allow us to uncover fundamental and novel insights on the value of even observing one single conversion rate at the fixed price point. So let me now illustrate the implications of our results. So in this graph, I'm going to show a mapping from the conversion rate to the guarantees that we obtain. And so despite the relevance of this data structure, there is only one known result that is related to this setting, where in the work by Azar and Al in 2012, they show that one cannot do better, so it's an upper bound, cannot do better than 50% of optimal performance using deterministic mechanism. Now, here we present the obtained guarantees for deterministic mechanism against regular distribution. So the first interesting observation here is that for a large band of available data, for example, if we observe a conversion rate that is between 10% to 60%, then we can guarantee a revenue that is higher than 50% of Oracle performance if we have this range. We also observe the asymmetry of value of information for low and high conversion rates, where for low conversion rates, the dependency is supralinear in order of square root of Q. And for high conversion rates, the dependency is 1 minus Q is linear. Now let us see what happens when we extend the set of mechanism to arbitrarily randomized mechanism. So we can see here that randomization actually changes the value of information for low and high conversion rates, as it goes from square root of Q to 1 over log of 1 over Q for low conversion rates. And also for high conversion rates, it changes the economics of data from 1 minus Q to 1 over log of 1 minus Q. So this both highlights the value of randomization as well as the value of low conversion rates. So for example, here, if we observe that just 1% of customers actually bought at the posted price, meaning that we have been pricing at a very high price, then we can still actually guarantee a non-trivial fraction of the optimal revenue as high as 31% using randomized mechanism and 18% using deterministic mechanism. Now we can also apply our framework to monotone hazard rate distributions. And the value of percentile information is actually quite striking again. So for a large band of data, if our conversion rate is from 20% to 70%, then we can get more than 70% of the optimal revenue. And one surprisingly high guarantee is, for example, if we observe just the median of the distribution, then we can implement a simple mechanism, a simple deterministic mechanism that will guarantee 85% of the optimal revenue with just one single observation. Now, for the impact of randomization, the impact is similar as the one observed for regular case, where the randomization allows one to actually change the economics of data. So for example, for high conversion rates, we move from linear conversions to 0 to 1 over log of 1 minus Q. And for low conversion rates, there is no real impact of randomization. And the value of low conversion rates is also significant, as in the case of regular distribution, where, for example, here, if we observe just 1% of customers bought, then we can guarantee 51% of optimal revenue with just this observation. So as we saw here, there is a significant information encoded in such data and information structure. And I will briefly discuss the approach that we have used to develop and characterize such performance. So we can formulate this as a mathematical problem where there are two important features. So the seller is optimizing over the set of mechanisms, which is in the case of randomized mechanism, is an infinite dimensional space. And nature is constraining the seller using all distributions that belong to the considered class of distributions. And both of these classes, like the regular and the MHR distributions, are also infinite dimensional. So it's an infinite dimensional space mathematical program, both in terms of the decision variables and also in terms of the constraints. So for the sake of time, I will not be able to go through the details of the approach, but I will give you a high-level overview of the method that we have used. So the first crucial step that we show is that one can actually reduce the set of constraints into a one-dimensional set by removing redundant constraints through a suitable parameterization, using the optimal reserve price and the structural properties of the considered class of distributions. And building on this result, we are able to show that for deterministic mechanisms, there are 3 regimes of conversion rates and can characterize in closed form the optimal price to post and its associated performance. For randomized mechanisms, we show that the space of mechanisms can be approximated by discrete mechanisms with bounded support. And in turn, we derive a linear program that approximates from below the max-min ratio and converges to it as discretization shrinks. So let me present here the result that we obtained for regular distributions and deterministic mechanisms. So we can characterize this optimal mechanism and its performance in closed form. And the price, the optimal price here takes form of 3 regimes. For high percentiles, it simply posted the price, and for smaller ones, it posted a price that is smaller than the observed price. And we can also characterize the exact optimal guarantees. And this is an example of the optimal deterministic mechanisms that we post. So as a summary, The most important takeaway to keep in mind is that percentiles and conversion rates, even if they don't give us a lot of information about the distribution of values of customers, they are extremely valuable from a pricing perspective. And the second important takeaway is that small percentiles have surprisingly very high pricing information content compared to higher percentiles. And the third important point is that randomization for some settings for high conversion rates can actually lead to significant improvements in terms of performance. And this opens up many new interesting questions. For example, how can one use these pricing mechanisms in order to warm start learning customers' behavior? And also, how can one use this to design near optimal experimentation? So thank you very much for your attention, and the paper is available in SSRN under the title Optimal Pricing with a single.